Welcome back all of you. In the last couple of classes, we discussed a lot about relaxation. That is one of the important concepts, very fairly a tough concept to understand. It is not pretty simple. I tried to explain in the most simplest possible way the two important relaxation phenomena in NMR called spin lattice relaxation and spin relaxation. Both of them we discussed a lot. What are those phenomena? What is that which is responsible for spins to relax? For example, in the case of the T1, we knew it is an energy, spins gives energy to the lattice. How it gives energy? What is the mode of giving energy? What is the form it gives energy? It is in the form of heat. What is the process which is responsible for the spins to give to the energy to the lattice? We discussed it. It requires a lot of other phenomena like fluctuating magnetic field, which is at the Larmor frequency. Then it so happens, then spins will give its energy to the lattice. And of course, what is the energy conserving phenomena while giving the energy to the lattice? And then what is the several phenomena which are responsible for spin lattice relaxation to happen? We discussed. For example, dipole-dipole interaction, chemical shift anisotropy interaction, that is CSA, spin rotation relaxation, quadrupolar relaxation. Various phenomena are responsible for the spins to give energy to the lattice and undergo relaxation. Similarly, we also discussed lot about spin relaxation. Spin relaxation also, of course, there is no energy giving to the lattice, but spins between themselves, there is a mutual interaction. It is nothing but a decoherence of the nuclear spins. For the reason, as soon as apply 90 pulse, bring the magnetization to x axis, instantaneously there is a statistical phase coherence. But what is going to happen is this all the magnetization vectors start dephasing with time. They will not be at the same place because of some local fluctuating fields, some local phenomena. As a consequence, the spins start moving, fanning outside all across in the xy plane. And then the intensity of the magnetization that you are going to get along the particular axis where you have receiver, if you take the vector addition of all the magnetic moment vectors, this keeps coming down. After some time, there is a complete dephasing, you will not see any signal. This phenomena is called T2 spin relaxation. It is a decay in the magnet in the xy plane. The spin lattice relaxation is the growth along exponential along z axis. Both are exponential functions. That is what we said. Both are exponential function. One is the decay function and the growth function. And we know that we said relaxation is a radiationless transition. In the case of this relaxation, how do you make the measurements? There are several ways of making the measurement of T1, and also for T2 we do spin echo sequence. See Corpuscle method, a Corpuscle modified Maibum-Gill modified sequence, or in the case of spin lattice relaxation measurement, we use what is called inversion recovery, where you apply 180 pulse, bring the magnetization to minus z axis, allow it to go back to z axis as a function of time. The magnetization vector, the magnetization starts shrinking along z minus z axis, slowly becomes 0 and goes towards plus z axis. This shrinking phenomena, how it shrinks, we can measure it as a function of time, and then fit it into the curve equation which is given for relaxation phenomena which you worked out. You will get the T1 values for all the peaks present in the sample. Same way we can do for the T2 measurement. Apply instead of 180 90, here is 90 180. First apply 90 pulse, bring the magnetization to x axis or xy plane, they start dephasing. Apply 180 pulse and vary this delay at this echo time, and after equal amount of time start collecting the signal, it forms an echo. Now you apply number of such echo sequences, and during the echo process what happens, there is a decay of the signal intensity due to natural process. You have to subtract the component from the magnetic field inhomogeneity and pulse imperfections. Then you again fit into the curve e to the power of mx or my equal to mz into e to the power of minus t by t2. Then you can measure the T2. So we understood quite a bit about how to make the measurement of relaxation, etc. These are all very important concepts. Using this, we can jump onto another topic called nuclear overarousal effect. That is something which let us try to understand. What is a nuclear overarousal effect? In this thing short, it is called NOE. It is also a fairly difficult topic to understand. Let us see how we can make it simplified to understand. Before that, we will understand what is the decoupling, which we discussed this in the previous class. There is no need to discuss in depth in this class, but let me tell you in the previous course. What is the decoupling? Is the radiation at a particular frequency of one nucleus to break its coupling with other. In fact, I mentioned this when I was discussing carbon-13 NMR. Remember, I said the broadband decoupling. When you detect carbon-13, you apply a radio frequency power RF pulse at the proton frequency such that simultaneously you will break the coupling with all carbons with all protons. Then you are going to get single peak for each carbon, of course excluding any other spins which are coupled to it. If there are no other spins coupled, if you break the carbons breaking with all the protons, you will get single peak for each carbon. That is a decoupling phenomenon. That is a broadband decoupling. So this is what exactly happens. Decoupling, when you do by applying the frequency at the site of the other nucleus, you can break the coupling between these two nuclei. It could be homonuclear or heteronuclear, both are possible. Okay, both can be. You can do homonuclear decoupling and heteronuclear decoupling also. And of course, this decoupling can be selective and broadband. In the case of carbon-13, there is a broadband decoupling. All carbons are decoupled simultaneously with all the protons. That is a broadband decoupling, and it covers the whole range of frequencies. Whereas in the case of homonuclear, that broadband decoupling is not possible, because you have to apply the decoupling power when the magnetization in the transverse plane. It is not possible to do without disturbing these spins. So there is a way to do that, that is called pure shift experiment, which I come to that if there is time at a later stage. We will discuss pure shift also, touch upon it at least. But in the case of homonuclear, even from the early days of NMR, there was one thing which was practiced. It was called selective decoupling. In the sense, if there is a complexity of the spectrum, what we do is selectively irradiate at a particular proton, selectively with a little RF power sufficiently larger to break the coupling between that proton with the another proton which is coupled to it. Then you see the effect of this multiplicity pattern if there is any change at the site of the other nucleus. Let us say I have one proton here, other proton here. You apply a small radio frequency pulse here like this at the proton H1, and you see the effect on the proton H2. So what is the meaning of decoupling is, I am saturating the spin states between one particular proton which I am irradiating. See exactly what we did in the broadband decoupling. We saturate the spin states, two spin states of the spin of nuclei, and it so happen spins will be going up and down, alpha to beta, beta to alpha simultaneously and so rapidly. The spin which is coupled to it will not see the spin either in the alpha state or in the beta state, in neither of them. It is the average field. As a consequence, what is going to happen? This will not couple to this, or in other words we say this proton is decoupled from that, because it is not seeing two different fields corresponding to two spin orientations alpha and beta of the coupled spin. This is what is called a homonuclear decoupling, selective decoupling. I can do if there are 10 spins, 10 different protons chemical inequivalent, I can irradiate only this and see the effect somewhere here, and these I do not touch upon at all. But if there is a coupling with this, effect is seen, but I will not touch that proton. That spins I am not touching at all. This is called selective decoupling. It is possible to do that, selective decoupling. Okay. In the heteronuclear case, of course, as I said, look at the carbon-13, do decoupling with proton or fluorine, any other nuclei. It need not be carbon and proton. Anything you can break. You saturate one of the nuclei in which you want to break the coupling. Carbon-13 usually in organic systems, we have plenty of carbons and plenty of protons coupled among themselves. What we do is we apply a broadband radio frequency, wide frequency over the wide range at a particular RF power for this proton, and saturate the spin system of these protons, population bit of these two energy states, and then see the effect of this at the carbon-13, and this is what you are going to detect. You apply the RF power here, strong RF power which is larger than the coupling strength, break the coupling, again make the spin states spins to undergo transition rapidly between two spin states, so that the carbon 13 will not see any of the protons in either alpha or beta state, and apply a detective pulse at this carbon 13 and detect the signal. This is heteronuclear decoupling. Okay. Now, when you are doing decoupling, some funny things do happen. What are these things which can happen? Effects of decoupling. First thing, the disappearance of multiplier of signal of S. It will instantaneously disappear, because you are saturating. That decoupling means saturation. I know I am saturating these two spins when I am decoupling. I will not see the signal. When they are saturated, there is no population difference. So, always decoupled spin will not give any signal. That is the first thing. So, it will disappear. You do not see signal at all. Okay. So, when I am irradiating RF at some chemical state of I spin, let us say, which is coupled to S spin, and the coupling constant is JIS, my decoupling power should be larger than this coupling strength. Only then this phenomena happens. There is a disappearance of the signal. That can happen only when this coupling, the rate in the RF is larger than coupling strength. Okay. Sometimes it so happens, if your decoupling power is sufficiently not larger, there is a reduction in the coupling strength. There is a reduced coupling you will see. Instead of this coupling, instead of becoming 0 and give you a single peak at the center, you may get a reduced coupling like this. This doublet, larger doublet will become smaller doublet like this. This is reduction of the coupling between I and this S spins. When can it happen? It can happen when the RF power is smaller than IS, much smaller. It should be very much larger than IS to break the coupling. If it is smaller, some funny thing will happen. Then the radiation frequency at that this thing is not exactly on resonance also, or when it is smaller than the coupling strength. In other words, what I am telling is, generally when you do the decoupling, you have to see that you apply the RF power exactly at the center of the coupled spin. That is what is the condition. Okay. So, what I am going to show now here is called, see, I have two doublets which are two protons which are coupled. I irradiate the center and the power should be larger than this, then this will become a singlet and no signal for this. That is this situation. Now, I have irradiated not at the center, somewhere here, far away, slightly far away, that is called off resonance. Off resonance irradiated, then it will happen, it will not become a single peak, there is a reduced coupling here. It will not become totally 0. Doublet will not disappear. That is one thing. Or you irradiate the same place, but the power is less, not sufficiently larger than JIS, then also it can happen. So, these are all the side effects of decoupling. It can happen, it can disappear, peak can completely disappear, the coupled peak will become a doublet, doublet will become a singlet, or the doublet strength comes down. That is one thing, when the power is less or when you are at off resonance, not exactly on resonance. Okay. This is the situation like this. See, when I am irradiating exactly at the center of A, intensity is exactly, see, all are equal. This is the chemical state of A, chemical state of X, this is JAX. This we discussed when we understood the Popel notation. Now, I am irradiating proton A. Obviously, I do not see signal because peak A is saturated, that we know, right. As a consequence, I do not see any signal at all. But nevertheless, there is a collapse of the doublet into a singlet. This is what at the chemical sheet of X, exactly at the center, that can happen. See, another side effect of decoupling is there is a change in the intensity of the observed peak which is not irradiated due to change in the population of the other spin. Okay. See, I am irradiating this spin A, and spin X I am not irradiating. I irradiate this spin and I see the change in the intensity of the signal. The change could be either increase or decrease. It can go up or it can come down. There is another thing it can happen. It is the effect of decoupling that can also be seen. change in the intensity of the observed peak, non-irradiated, due to change in the population of the irradiated spin. It can happen. Okay. And of course, there is another thing, phenomena, which I did not discuss. It so happens neither the peak will disappear, nor there is a reduction in the coupling strength. It can happen, you will get additional peak, more peaks in NMR. It's funny thing can happen. You are irradiating one peak, in the coupled proton if you see other proton, instead of reduced intensity or a complete nullification of the reduced coupling strength or complete nullification, you get additional peaks will come. That is the phenomena called spin tickling. We will not worry about those things, but what I wanted, we are concerned is, our main interest is to see the change in the intensity of the non-irradiated peak. This is the important point. I am irradiating one peak, seeing the change in the intensity of the other proton. This effect, the change could be positive or negative, whatever it is, this effect is called nuclear Overhauser effect. It is an effect called NOE, nuclear Overhauser effect. And interesting point you should know, for this nuclear Overhauser effect phenomenon, NOE is the spins need not be J coupled. When we were decoupling, I said the spins were coupled and we were breaking the coupling between them by using the second RF. Okay, irradiating RF at a strength larger than the coupling strength, we broke the coupling and made it completely decoupled. That is a decoupling, broadband and selective. But for NOE phenomena, I irradiate a peak and see the change in the intensity of the other, but the spins need not be J coupled. Very interesting. So, if they are not J coupled, you may ask me a question, then how does the intensity change occurs? But remember, what is important is not J coupling, but the spatial proximity. The two spins should be very close, preferably less than 5 angstroms, it should be there. Then NOE can be seen. Spatial proximity is important. No matter how far they are separated, see in a 3-dimensional configuration, conformation, it so happen one proton may be here, it undergoes conformation etc., and other proton which may be separated with 10, 20 chemical bonds may come close to each other in space, in a 3-dimensional space. Does not matter. As long as they are close in space, then this phenomena can happen, this NOA phenomena can happen, and there is a change in intensity you observe. Okay? That is important point. Now, when the increase of intensity I takes place, we call it as a positive NOE case. The intensity is I increases, we say there is a positive NOE. If the intensity I decreases, we say the NOE is negative. Both can happen. You understand the concept now. Important point, for NOE, spins need not be J coupled. What is important is spatial proximity. When you irradiate one spin, there is a change in the intensity of the other spin. If the intensity is increased, a positive NOE. If the intensity of the other spin decreases, it is negative NOE. These are the concepts you must remember. Then how this NOE developed? How did we come to know this phenomena? Little bit of some historical about NOE, because it is needed. We should know how it was discovered by stalwarts, great scientists. They discovered this thing and made our life simple to understand. So, this is NOE, little bit about this thing. It was predicted by Overhauser. That is why it is called nuclear Overhauser effect. Remember, he predicted this in 1950s, nearly 70 years back itself he said this. What a genius idea. See, those days itself he was able to predict this can happen. What he did was not with nucleus and nuclear spins. What he did was, he says saturation of a conducting electron if it is there in the metal, a conducting electron spin if it is there in a metal, you saturate that. Then he says nuclear spins get polarized 1000 times more. Marvelous phenomena. Remember, NMR detection is very sensitivity is a big issue, less sensitive. We have been discussing NMR is a less sensitive technique, compared to all other molecular spectroscopic technique. But look at this idea. We have nuclear spins, we have electron. He says saturate the electrons. Okay, electron spin of particular metal, if you conducting electron, let us say conduction electron, if you are going to saturate that spin of that electron in a metal, he says the nuclear spins will gain polarization. The polarization gained by nuclear spin is 1000 times more. Marvelous idea. So, and this implication means the population of the nuclear spins is enhanced 1000 times because the electron spin polarization is transferred to nuclear spin. There is no coupling between these two. There is no, but nevertheless, there is a nuclear electron spin directly transfer the polarization to nuclear spin. So, nuclear spins acquire electron spin polarization. As a consequence, its intensity goes up by 1000 times. If you calculate by Boltzmann population distribution, electron population, Boltzmann population is much larger compared to nuclear spins. So, nuclear spins now attain electron spin Boltzmann population, and that is why the detection sensitivity enhanced by 1000 times. And this was a brilliant idea given by Overhauser. He did not say irradiate one spin and observe the change in the other nuclear spin, but what he said is saturate the electron spins in a conduction electron of a metal. Then you see the nuclear spin will attain electron Boltzmann population and enhances the intensity by nearly 1000 times. This is the idea given by Overhauser in 1950s. Okay. And the population difference is enhanced by 1000-fold. Now, the interesting thing is you did not increase the magnetic field externally. Remember, I told you we started increasing the magnetic field, and we gave one slide, I gave an example. As you keep on increasing the magnetic field, the energy separation keeps increasing, and the population difference also changes linearly with the magnetic field. We even calculated for different magnetic field what is the population difference between two different energy states. So, now 1000-fold change without increasing the magnetic field, it is a phenomenal achievement that was done. So, the nuclear spins acquired electron spin population without even enhancing the magnetic field, and this was demonstrated experimentally by another person called Carver, and he really saw that he saturated the electron spin and observed the change in the intensity of the nuclear spin by experimentally. He really observed that it was phenomena not just predicted. Overhauser predicted that, but Carver observed that, and this was named dynamic polarization. Dynamic polarization happens. Why dynamics? Because as soon as you saturate, nuclear spin get attain Boltzmann population of electrons. Dynamically it happens. So, this was called dynamic polarization. And there was another scientist, Solomon. Solomon, what he did was, he showed this form of polarization transfer need not be for metals between electrons and nuclei. It is not restricted only to the metal. It need not be between electron and nuclei. You do not have to saturate electrons and enhance the nuclear spin polarization. He said it is possible to transfer polarization from nucleus to nucleus also. Irradiate one nucleus and see the change in the intensity of the other. It's exactly identical phenomena. But only thing is here the Boltzmann population is not electron Boltzmann population. It is a different phenomena here. Same nuclear spin, you are at small change in the intensity, not 1000-fold, but minimum small change. We will see how much is the change in the intensity. We can work out as we go ahead in this class or in the next class. We will see what is the change in the intensity. So, it is possible not only for transfer the polarization from electron to nucleus, he showed it is possible to transfer from nuclear spin to nuclear spin. Irradiate one nuclear spin, see the polarization transfer to other nuclear spin, change in the enhancement in the intensity of that particular spin. Okay. So, with this we will try to see some salient points of NOE. Each of these points we will discuss as much as possible. I will take all of you through this slowly and steadily. As much as possible we will discuss each point. Salient points of NOE. One is, it depends upon dipole-dipole relaxation. Of course, we discussed this in relaxation. That is why I introduced relaxation before NOE. It is an important mechanism. It is a dominant mechanism for relaxation, especially spin lattice relaxation we discussed. Dipole-dipole interaction is a dominant relaxation mechanism, especially for spin of nuclei. For T1, we saw that. We know that nuclear spin undergoes molecular motion. Its orientation with respect to the magnetic field do not change between the two nuclear spins. They orient with respect to the magnetic field remain same, but because molecules are undergoing tumbling, there is a change in the local field situated or generated at the side of the other spin, which has a frequency analogous to Larmor frequency. If you can calculate the frequency of that motion, that induces transfer of energy from spin to lattice. That we observed. The dominant dipole-dipole interaction phenomena. That is one of the relaxation phenomena dominant in NOE. NOE is dipole-dipole relaxation phenomena, and it is due to through space interaction. There is no need of a chemical bond. I told you already, what is needed is the spatial proximity of the two nuclear spins. They should be close in space. That is enough. If they are far away, there is no transfer of polarization. So, for this to happen, the spin should come close in space. Then the energy transfer takes place. This polarization transfer takes place. And see the gain in intensity. And so, it is not through covalent bond, it is a direct through space interaction. It is through space. That is one point. And NOE changes intensity of the particular signal, only particular signal. If you are irradiating particular signal, it changes the intensity of the other spin which is in close proximity. Something else which is far away, which is not connected to this, will not affect at all. It will affect the intensity of something which is close in space. It will change, increase or decrease. Only particular spin it will change intensity. And the magnitude of this NOE is related to nuclear distances and molecular motions. That is correct. I told you spatial proximity is an important phenomena. Farther the distance, as we go ahead, I will tell you NOE depends upon 1 over r to the power of 6. If the distance slightly increases to the power of 6 in the denominator, so drastically the intensity of the signal comes down. The polarization transfer will not take place. So, NOE phenomena depends upon the distance between two spins, which is the inverse of r power 6. That is another thing. And of course, it also depends upon the molecular motions we know, because relaxation of dipole relaxation, everything we discussed about spectral density function, everything we will talk about it this time also. If there is a time, we have to talk about those things. So, these are all some of the important points. The magnitude of the NOE is dependent on the nuclear spin distances and enhancement in the signal intensity. There is a change in the intensity of the signal. It depends upon several factors. One thing, of course, distance between the interacting spins, which we discussed. I already said it is 1 over r power 6. That is one thing. And it depends upon the mobility of the molecule tau c. Of course, we discussed about this tau c, JW, everything earlier. Tau c depends upon the size of the molecule, depends upon molecular mobility. Most important thing, it also depends upon magnetic field and Larmor frequency. That is what we discussed, omega tau c. We discussed omega tau c condition, which is greater than 1, equal to 1, less than 1, what will happen? For small molecule, big molecules, medium size molecules, we discussed during relaxation. So, it depends upon the magnetic field. In other words, it depends upon omega 0, Larmor frequency. And also, most important thing, it depends upon various pathways available for relaxation. The relaxation phenomena we discussed, mechanism involved in relaxation we understood. There are several pathways the spins can relax. What are those pathways? What are those pathways? How the nuclear spin undergoing? How if it relaxes in a particular pathway, how is there the change in intensity changes? This is the most important thing you have to understand. Actually, this is the origin of NOE. The origin of NOE is how the nuclear spin relax, which is a pathway it adapts for relaxation. That defines. So, NOE enhancement intensity of the NOE depends upon several factors. Many things are there which we will discuss, but most important point is it depends upon the relaxation pathway which is available, which is the dominant relaxation pathway, and it depends upon the Larmor frequency. For example, if I do the experiment at 600 megahertz spectrometer, the same NOE you may not get at 200 megahertz. Larmor frequencies are different, enormously different. 200 megahertz is omega is 200 here, they are at 600 megahertz, quite a bit, nearly 3 times larger. Similarly, mobility, it depends. A big molecule like protein may give rise to NOE in a different way compared to a small molecule. It also depends upon distance. So, these are the important factors, parameters which dictate the change in the intensity because of NOE. So, what we do is we will discuss about the dipolar interaction and various things, what will happen, everything later. But now since the time is getting up, what I am going to do is I will stop today. What we discussed today is, after discussing all about relaxation, everything last class, we started jumping into understanding what is NOE. NOE, as I said, is a nuclear Overhauser effect. It was predicted by Overhauser in the year during 1950s itself. He said, saturate an electron, conducting electron of a metal, you will see the polarization of the nuclear spin gets enhanced by 1000 times. This is a marvelous, remarkable phenomenon. The nuclear spins now attain electrons Boltzmann population. This is what we understood, right? So, electron Boltzmann population will be attained by nuclear spins. So, after some time, few other stalwarts said it need not be restricted to electrons and nucleus, it can be between two nuclear spins also. That is also possible. NOE, Overhauser, like Overhauser predicted, enhancement of the signal intensity is also possible between two nuclear spins, not only restricted to electrons and nuclear spins. This was also demonstrated, but the only thing is Boltzmann factor is not electronic Boltzmann factor this time. That is a different question, but still there is a enhancement, and enhancement of NOE depends upon various factors. The factors depends upon pathways available for relaxation, and it depends upon the Larmor frequency, depends upon the mobility of the molecule tau c, and distance between the interacting spins, and various factors are responsible for understanding this NOE. They contribute for the change in the NOE. So, each of these things we will discuss in the next class. So, I will stop today. In the next class we will continue further. What are the relaxation pathways, how it affects everything, we will discuss in detail later. Thank you.